preservability.
Hey, thank you. Yeah, so I did this work with Chung-Yui and Paul at the University of Bristol. Okay, so a summary of this result would be that it's a framework with which we can compare the ability of noisy operations to preserve informational non-equilibrium of states for all states in the state space.
If your mic is not turned on.
Is it not? Yeah, okay. Okay, so the notion of informational non-equilibrium comes from the resource theory of informational non-equilibrium, in which the resource is some measure of how far away you are from the maximum mixed state. And I'll come around and talk a little bit more about what that is later. So yeah, just a quick overview. I'll go through our aims, our framework, and then the results. But just a quick word on notation. So when referring to static resource theories, I'll have a superscript of ST. And in this case, the allowed operations will be some set of quantum channels, and the free set will be some set of quantum states. When considering dynamical resource theories, I'll have a superscript dyn, where now our allowed operations will be some set of quantum channels, and our free objects will be some set of quantum channels, so some super channels and some set of quantum channels. Okay, so what we set out to do was build what's called a resource preservability theory. So this was an idea pioneered by Chung-Yui while he was doing his PhD at ICFO. And so a resource preservability theory, it's a dynamical resource theory, and each static resource theory induces a dynamical resource theory of preservability. And the idea is that it's used to study the maintenance of a resource in some static resource theory. So here's my graphical depiction of a static resource theory. You have some set of all states for which some are free, and then you have some subset of all channels which you say are allowed operations. And these might be defined based on the physical constraints of your system. And our resource preservability theory exists entirely within the same set of constraints. So we have the same set of allowed operations, and now we're defining a new resource theory within this. And so now within our allowed operations, we say some set of channels are now free. So these are going to be the channels that can't preserve any resource. And then we define some subset of our allowed operations that map us from our allowed operations of our static resource theory to other operations of our allowed static resource theory. So we remain fully inside this universe of the physical constraints of our underlying static theory. Okay. So what is it that makes a channel resourceful in one of these resource preservability theories? So if we have some allowed operation that's mapping us between two states, and both of these states are resourceful, such that we're starting outside this free set and we're remaining outside this free set, then we'll say that the channel N has some amount of resource. And so if this is true for even just one input state row, then we say that our channel is resourceful. So for some resourceful state, we're able to preserve some amount of resource in that state when we act on it. Okay, we're good. Okay, so what does it mean to be resourceless? So if we input some resourceful state, then we're always getting out some resourceless state. So we're always mapping to be inside this free set. And we say if this is true for every state in the state space, so regardless of how resourceful the state we're putting in, we're always getting out a state that is resourceless, then we say that we have a resourceless channel. So what these resourceless channels are their state preparation channels of the channels in our underlying static resource theory. Okay? And so these are states for regardless of what state you put in, you're always getting a resourceless state out. So what are the allowed operations of this resource preservability theory? So there's some super channels, and they map allowed operations of the static resource theory to allowed operations, such that we're remaining inside this universe of our static resource theory. And they have to be dynamical resource non-increasing. So if an allowed operation exists between two channels, it has to be the case that the static resource content of our output channel N is always less than or equal to the static resource content of our input channel N for all states in the state space. So there's no states for which the resource can be preserved more from our output channel rather than our input channel. So just a summary of what these theories are then. So there are dynamical resource theories. Each static resource theory induces one of these resource preservability theories, and it's used to study the maintenance of a resource in a static resource theory. And so I would sum this up by saying that a preservability theory applies structure to the set of allowed operations of a static resource theory based on the ability of those allowed operations to preserve the static resource. And by structure, I mean some pre-order applied to this set of allowed operations. Okay, so The static resource theory that we chose to build one of these preservability theories on was the resource theory of informational non-equilibrium. And so within this theory, the allowed operations that the agent can implement are some unitary, preparing a system in the maximally mixed state, and then taking the partial trace. And so these allowed operations look like this, and they're called in the literature noisy operations. And now the convertibility power of these noisy operations are the same as the convertibility power of the set of unital operations. So we learned in the talk yesterday that these are in fact not the same set, but their convertibility power is the same. And so considering the fact that in this work we're only talking about convertibility, we'll talk about noisy operations as unital operations. And so no surprise that the set of states for which these noisy operations are invariant are then the maximally mixed state. Okay, so we'll sum this up as our underlying static resource theory. It's going to have allowed operations of unital channels and the free set of the maximally mixed state. So the reason why we chose this to be our underlying static resource theory in which to build our preservability theory is firstly that it's the most mathematically and physically simple resource theory that we can think of. And if we want to build one of these dynamical resource theories, we thought it'd be easiest to do it off this simplest example of a resource theory. And on top of that, it's also a special case of the resource theory of thermodynamics, as again we heard yesterday, where if I take my thermal state and I consider a completely degenerate Hamiltonian, my thermal state becomes the maximally mixed state. And then what this can be interpreted as is an isolation of the informational contributions to thermodynamics. So you get rid of all your energetic contributions and anything you have is just some informational change. And then maybe we can use this as a foundation on which to build a resource theory of athermality preserving channels in the future. Okay, so that's our underlying static resource theory up in the top corner there. So what about the induced resource preservability theory? So as I said, that the free channels of our resource preservability theory are state preparation channels of the free states in our underlying static resource theory. So in that case, we only have one free channel, one free state in our static resource theory. So our free channel of our dynamical resource theory is the state preparation channel of the maximum mixed state. And then the allowed operations we consider of this form, I can talk a little bit more offline if people want to talk about how we came to this conclusion, but we just have some pre-processing and post-processing channel, which are both noisy operations. And so we can see that this fits our criteria. It maps noisy operations to noisy operations, because some concatenation of free operations is itself just a free operation. And in addition to this, it's dynamical resource non-increasing. So for every possible input state to pi n, that's going to have less resource than any possible any input state to n, due to the fact that p and epsilon are themselves resource non-increasing. Okay, so this fits our criteria. And then for the allowed superchannels, we just take the convex hull of these operations. So I can sum up our resource preservability theory as our allowed operations are the convex hull of operations of this form, this pre and post processing channel, and then our free set is the state preparation channel of the maximally mixed state. Okay, so a summary of our framework. This is our underlying static resource theory, and this is our dynamical resource theory of informational non-equilibrium preservability. And then we could also write these free operations in some choice state formalism, where we have some pre and post processing noisy operation, which acts on the subspaces of this channel. Okay, so the ultimate question that we're looking to answer is some characterization of this resource theory. So if I give you two noisy operations, does there exist an allowed operation of my dynamical resource theory that maps me from one to the other? And if so, I can say that M has less dynamical resource than N, which means that the ability of M to preserve informational non-equilibrium is less than or equal to the ability of N to preserve informational non-equilibrium. And then physically, that's going to mean that for every possible output state of M rho is going to be have less informational non-equilibrium than the same state output from N rho. Okay. So just quickly before we go into some results from this framework, we take the following restriction that we consider noisy operations with equal input and output dimension. So we did this because we wanted to consider systems evolving, and we felt like this was a realistic assumption to make, but it also simplifies the math somewhat. So previously I said that the convertibility power of noisy operations was the same as unitals, such that if I can find a noisy operation mapping me between two channels, I can also find a unital that maps me between those two states, and vice versa. But if we could take this consideration of equal input and output dimension, then this unital channel becomes some mixed unitary channel. And so then I can sum up my static resource theory now as having the free set of being some, the allowed operations rather, being some mixed unitary channel, and the free set, again, being the maximally mixed state. But in addition to this is also the regime in which the resource theory of informational non-equilibrium and purity align. So from here on out, if you'd be more comfortable considering informational non-equilibrium as purity, you're welcome to. Okay, so what results have we got in this framework? So the summary of this convertibility criteria is as follows. So if we take some spectrum of the choice state of our target channel N, and if we can find some convex combination of local permutation matrices that maps us to a vector of the eigenvalues of our output state M, then we know that the allowed operation of our dynamical resource theory exists. And this is an if and only if condition. So what we do is if you give me two channels N and M, which are allowed operations for my static resource theory, I find the choice state of these two channels and I diagonalize them and then put their eigenvalues in a vector. And then I ask whether or not there exists a matrix, which is a convex combination of local permutation matrices between these two vectors. If so, I know that this relationship exists between their choice states and ultimately an allowed operation exists. And as I say, this condition is if and only if. And for those people familiar with the static resource theory of informational non-equilibrium, the convertibility criteria is the fact that the target channel must, the spectrum of the target state must majorize the spectrum of the output state, which is then, of course, some doubly stochastic matrix, which is itself a convex combination of permutations. So this convertibility criteria has a similar flavor to the underlying static resource theory, which is nice. But also it has this nice geometrical interpretation. So if I write out this convex combination of local permutation matrices acting on these vectors, I can get rid of the final value due to the normalization. And all of these vectors are now three-dimensional vectors of real values. And so I can plot these in some three-dimensional space where each point in this space is some three-dimensional representation of a qubit noisy operation. Okay, and all my unitary channels have some unitary degrees of freedom in my proof. So they all map to this point down here, and then the other outer points of this tetrahedron are the local permutations of that unitary representation. And so now my target channel is represented by some three-dimensional vector for which this inner tetrahedron represents the local permutations of those. And then this pink region is the convex hull. And then in the center here, I have my free channel, which is my state preparation channel of the maximally mixed state. And then I can ask the question of whether or not an allowed operation exists based on whether or not the three-dimensional point that represents my target channel sits inside or outside of this convex hull. So if the three-dimensional representation of my channel M is this mu, I see that it sits inside this convex hull, so an allowed operation exists. If instead it's represented by mu, then I can see it sits outside, and so I know no allowed operation exists. And so from this picture, we managed to find a set of 4 inequalities that were a complete set of monotones, and we were able to find a set of 4 states that can be used in a state discrimination task that fully characterizes this partial order. And so what we're doing here is we're finding planes that encompass each of the faces of this tetrahedron, and then we're asking on which side of these planes does our three-dimensional representation of our channel sit. And if it sits on the correct side for all 4 planes, the correct side being the side in which this free state or the free channel is, then we know that an allowed operation exists. Okay, so just a few examples that we applied this to, a few simple examples of the depolarizing channel and the dephasing channel, parameterized by S and Q respectively. And so the first few are just a bit of a sanity check. So I find that an allowed operation exists between the depolarizing channel to another depolarizing channel if S prime is less than S. And likewise, from a dephasing channel to another dephasing channel if Q prime is less than Q. Again, this makes sense. If I'm decreasing this parameter S, I'm decreasing the purity of the output or the amount of informational non-equilibrium in the output. And then if I want to go from a depolarizing channel to a dephasing channel, I find this is only possible if S is equal to 1, which means that this depolarizing channel is essentially just the identity, so it's in no sense depolarizing. So I say that no allowed operation exists between a depolarizing channel and dephasing channel. So physically, this means that regardless of my value of S and Q, I can always find some input state for which the output from the dephasing channel will be more pure than the output from the depolarizing channel. So if instead we're looking to go from a dephasing channel to a depolarizing channel, we find that we have to meet this bound, that S is less than or equal to Q over 2 minus Q. So as an example, if I take Q is equal to a half, I find S has to be less than a third for an allowed operation to exist. And so what does this look like in our geometrical picture? So there is my three-dimensional representation of my depolarizing channel, and the pink section is my convex hull of that represents my dephasing channel. And I see that if I take S is equal to a third, which sits on this boundary, then this point sits exactly on the boundary of this convex hull. And then if I was to decrease or increase R, I see that I move inside or outside of this convex hull. So an allowed operation does or doesn't exist. So we did manage to find an extension to d-dimensional channels in the form of Weyl covariant channels. So these are channels of this form at the top, where these W are Weyl-Heisenberg operators. And so these are a subset of unital channels in higher dimensions. And we found a result with a very similar flavor for the convertibility criteria, except now it's no longer just a convex combination of local permutations, but it's local cyclic permutations. And using a similar proof in terms of this geometrical structure, we're also able to find a set of d-squared inequalities that fully captured the partial order set by this preservability theory. And we're also able to find a set of d-squared states that you could use in some state discrimination task. So similar to our qubit result. So if you want to take this a bit further in the future, ultimately what we want to do is we want to be able to characterize this preservability theory for arbitrary d-dimensional channels. So currently we've done it for qubits and Weyl covariant channels, but we'd like to do it for all noisy operations acting on d-dimensional systems. But we'd also like to consider noisy operations that have differing input and output dimension. And finally, what we'd like to do is expand into the resource theory of thermodynamics, so away from static resource theory of informational non-equilibrium by turning on this Hamiltonian and having it not equal to 0. Okay, so the key takeaways would be that resource preservability theories apply structure to the set of allowed operations of a static resource theory, and that we characterized a resource theory of this type for the static resource theory of informational non-equilibrium, with the caveat that it was for qubit and d-dimensional Weyl covariant channels that have equal input and output dimension. And that ultimately that this framework can be used for the quantification and comparison of noisy operations ability to preserve informational non-equilibrium. Cheers.
Do we have any questions here? Hi, thanks for the nice talk. Can I ask you if this pre-processing super channel kind of structure, is that the one you kind of impose, or is it like the maximal thing you can do to like freely to not make this channel more resourceful?
Yeah, so it came from a structure like this where we have some super channel applied to our channel N. And then in this memory line of this super channel, we enforce a resource annihilating channel to prevent this, this super channel from being able to increase the amount of dynamical resource. But in answer to your question, I don't know whether or not this is the largest set of dynamical resource non-increasing channels, or whether it's some subset or the distance between the two.
I see. Thank you.
I'm not sure whether I understood your definition correctly. So you said the free channels in your dynamical resource theory, those are the resource destroying ones, right?
Yes.
But you also said those are the preparation channels for the free states. Like in a general resource theory, shouldn't those two sets be different?
So the free set of our resource preservability theory, so our static theory, they're the state preparation channels of the free set of our underlying dynamical static resource theory. And in the sense that that means that regardless of what input state I give you, the output state always has no resource. So in that sense, those channels never preserve any resource regardless of what your input state is.
Okay, but let's say we talk about coherence theory, right?
Mhm.
Then if I do defacing, the output is always incoherent, right? So I always get a free static state back. But that would not be a preparation channel, right? Because it depends on the input state in some sense. So for if you only have one free state, yes, of course, like that's the same, right? But in general,
Yeah.
it shouldn't be the same.
To be honest, I haven't put much thought to what it would be beyond thermodynamics, where we only have one free state. So yeah, I'm not sure.
Okay.
Yeah, but I'll talk to you about it afterwards.
Yeah, thanks.
Is it easy to extend your result to the asymptotic theory? What is the stumbling block to not to prevent extend your result to asymptotic form?
So when you say asymptotic, you mean like
Many channels to we want to transform many channels to many channels.
Oh, that's something that we've left for the future. We haven't considered multiple conversions of channels. We've left it in just a single shot case at the moment. But it's not something that we've thought about yet.
Thank you.
Any final questions?
Could you explain once again like what's happening between the steps A from the C? Like how do you get from A to C here?
Oh, AC. So P is some noisy operation where we're bringing in some maximum mixed state and doing some joint unitary on the input channel input state row and some bath that's a maximally mixed state. And then we end up this channel here is some state preparation channel of the maximally mixed state. So we'll just throw away this memory line and instead bring in another maximally mixed state. And then we can just roll that into a definition of another noisy operation. So we kind of ignore this memory line due to the fact that in step A, we have a state preparation channel, the maximally mixed state. So we chuck it away, bring in the new one, and then we roll this into one definition of a noisy operation, which we call E prime.
But is there a reason why you can't assume the memory line is like undergoing an ident channel? Like why do you have to? Why does the lambda have to be the state preparation channel? Is it because it's a free channel?
So it's a way to try and prevent. Let's say if you've got some resourceful state in P, you swap it onto your memory line using the pre-processing channel, and then maybe back onto your initial input state using epsilon, and then you've avoided putting your state through your channel N altogether. And then you worry about the fact that you might be able to increase the amount of dynamical resource because you haven't actually applied your state, your state N through your channel N. So it's to prevent it being dynamical resource increasing.
Okay, let's thank Benjamin again. And now we have a snack break, yes.